Welcome to your first video lesson on magnetism. By the end of this video, you will hopefully be able to explain the basic history of magnets along with scientists and their contributions to our understanding of magnets today. We'll also understand how magnetic fields work. So let's start by taking a trip back in time to ancient Greece in around the year 800 BC, where legend has it that a shepherd by the name of Magnus was curious as to why certain stones were attracted to the nails in his slippers and to his metal staff. This phenomenon, noticed by the shepherd Magnus, would be continued to be studied as time passed, and humans would develop a better understanding of what we now call magnetism. As the ancient Greeks continued their study of magnetism, they noticed that certain rocks would seem to want to touch each other if they were orientated in certain ways. And yet these same two rocks, orientated in a slightly different way, would repel each other and not want to touch. I want you to right now pause the video and come up with an explanation for this mysterious phenomenon that the Greeks noticed. Now, if you deduced based on previous science classes that this is based on magnetic poles, you are correct. It is this observation with the orientation of rocks that led to the law of magnetism, which states that like poles repel and unlike poles attract each other. So now what I want you to do is copy down these three different styles of magnets. And what I want you to do then is to pause the video and try and figure out what would be the possible north and south pole for each of the three magnets. So pause the video, and when you're done, come on back. Welcome back. So if I look at this, let's take a look at my first horseshoe magnet. The top here, I could say, is north. Now if the top is north, that would mean south would have to be the bottom part. These could be rearranged. They just have to be opposites. So if I said the top was south, the bottom would be north. Now let's look at this circular magnet. If I said on top was north, that would mean underneath the magnet would have to be south. Now let's look at my bar magnet. Here, if I say one end is north, then the other end would have to be south. So what is the story of how we got these names, north and south poles? Well, the names of the north and south pole can be accredited to Pierre de Maricourt. He started off by mapping positions of a magnetized needle around a magnetic rock. Here he observed that the direction of the needle encased the rock and converged at two opposite points. He then looked at, before he named these points, and he tied the rock on a string and noticed that those opposite points pointed in certain directions. If you put it on the string, the one end, where all the direction of the needle converged, pointed to the north, whereas the other end pointed to the south. He ended up calling these the north and south poles. And that's how we got the name North and South Pole. This is also how we got the name lodestone, or otherwise known as leading stone, for certain magnetized rocks, as they could help us find out which way is north and south. So the next big advancement came from William Gilbert in his book De Magnet. Now, the most important thing here to look at is how he compared the orientation of magnetized needles on the surface of a spherical piece of lodestone or magnetic stone with the north and south orientation of compass needles at various locations of Earth. From this study, he was able to propose that Earth itself is a lodestone with a north and south magnetic poles. So in other words, he proposed that Earth itself was a magnet. Now, I have a question for you here to answer. The north pole of a magnetic compass needle points towards the Earth magnetic north. What can you conclude about this point on Earth? I want you to think about this on what we learned so far and try and answer this in the class tomorrow. Now let's look at more what are magnetic fields. Magnetic fields surround a magnet and is represented by this symbol B and is measured in Teslas. Now, if we have a compass going around a magnetic field, we use that to figure out the direction of magnetic field lines. So following this compass here, we end up going at a direction kind of like this. And then we could say the same thing here. And it's going to go around that way. So by using a compass, it helped us figure out the direction of magnetic field lines, and that is why we go from a north to a south pole. Almost 200 years later, Michael Faraday further developed this concept. He defined a magnetic field as a three-dimensional region of magnetic influence surrounding a magnet, in which other magnets are affected by magnetic forces. The direction of the magnetic field at a given location is defined as the direction in which the north pole of a compass of a needle points at that location, much like what we've shown just before. He also explained how some materials, such as iron, act like magnets while in a magnetic field. Let's get back to Gilbert. His ideas about an invisible orb of virtue would revolutionize physics. I have some diagrams here which you need to understand and really know. So first we're going to look at a bar magnet. If we remember, we could figure out the direction of magnetic field lines by placing a compass. And we'll always know the direction of the compass, where it faces north, will be the direction of the magnetic field lines. So in this case, my magnetic field lines are going to always go from north to south. Now if I have two attracting poles, that means I need opposite poles. So I have a north and a south here. And remember, my field lines always go from a north to the direction of south. And then we have one more here when we have poles that repel. These must be identical field lines. In this case, I have two north poles where my field lines are coming out of the north. Just remember, they always go out from the north and to a south. So if I had two south poles, what would end up happening is my field lines would be going into the pole instead of out of the pole. It'll look exactly the same except the field lines are going in. So some key things to remember here is we always go out from the north and into the south. And another thing is the closer the field lines are together, the stronger the field. So if I go back up to this first image, my field lines are super close at the poles. That must mean my magnetic field strength is strongest at the poles. Right here, my magnetic lines are closer together in between the north and south as they go directly across. That must mean the magnetic field strength in this area must be stronger than the magnetic field strength in this area. And same with this last one here. I look at this, we have an area of no influence. My magnetic field lines are getting closer and closer. As I push these two magnets closer together, the magnetic field lines are going to get closer and closer together because they can't cross, which will make them stronger and repel each other with a greater force. So here I have 4 pictures of magnets and their magnetic field lines. I want you to copy down these pictures and copy down their magnetic field lines and also try and put in the direction of the magnetic field lines. Remember, they go from north to south.